something changed in the way the United States watches the invisible storm surrounding Earth. On August 21st, 2026, NOAA's Space Weather Prediction Center officially moved its new solar wind display out of its experimental phase and into operational service. That may sound like a software update. It is not. Solar wind is the constant stream of charged particles flowing away from the sun. And when that stream changes, the space around Earth can become much more active. Stay until the end because the most important part of this story is not the new screen itself. It is what that screen is designed to help scientists see before changing space weather reaches our planet. The announcement came from NOAA's Space Weather Prediction Center, or SWPC. The agency said the new display completed its experimental review period. The experimental banner was removed, making the display operational. Why does solar wind deserve its own monitoring system? Because the sun is not simply a ball of light sitting quietly in space. Its outer atmosphere continuously releases plasma. That plasma carries charged particles and magnetic fields outward through the solar system. Most of the time, Earth's magnetic field deflects and redirects this flow. But the solar wind is not perfectly steady. Its speed, density, temperature, and magnetic properties can change. Some changes are relatively weak. Others can become important when they interact with Earth's magnetosphere. This is where space weather begins to matter. When a stronger disturbance reaches Earth, it can compress the magnetosphere and drive currents through the near-Earth environment. These processes are connected with geomagnetic storms. During significant events, space weather effects can interfere with satellite operations, radio communication, navigation systems, and electrical infrastructure. They can also produce spectacular auroras at lower than usual latitudes, but there is an important distinction. A new monitoring display does not mean a dangerous solar storm is happening right now. NOAA's August 21st announcement was about the monitoring capability itself, not a declaration of an impending catastrophe. That distinction matters. The value of the system is timing. Scientists cannot stop a solar eruption after it happens. They cannot place a shield around every satellite. What they can do is measure conditions in space and watch how the solar wind evolves. Better observations can give forecasters a clearer picture of what is moving toward Earth and how strongly the solar wind may interact with our magnetic environment. Think of it like weather radar, but on a planetary scale. A weather radar does not create a storm and does not guarantee exactly where every raindrop will fall. It gives meteorologists measurements that help them understand what is happening and improve forecasts. Solar wind observations serve a similar scientific purpose, except the environment being monitored is millions of kilometers across and filled with charged particles and magnetic fields. NOAA already operates a broad space weather monitoring system. Its public data include measurements and products related to solar wind, geomagnetic conditions, auroral activity, and other parts of the Sun-Earth environment. The new operational display adds another way to visualize and interpret solar wind conditions. And this is becoming increasingly important. Modern society depends on systems that operate far above the ground. Communication satellites connect networks across continents. Navigation systems depend on signals traveling between spacecraft and receivers. Earth-observing satellites monitor weather, climate, oceans, and land. Crews and equipment in space also operate in an environment that is fundamentally different from the atmosphere below us. That means space weather is no longer just an astronomy problem. It is an infrastructure problem, and the sun does not need to be aimed directly at a city to create an effect. A disturbance can travel through interplanetary space, interact with Earth's magnetic field, and alter the conditions experienced by spacecraft and technological systems. The new display is therefore part of a larger scientific effort, turning a constantly changing solar environment into data that forecasters can understand quickly. But there is still a major question. How much warning can solar wind measurements actually provide when a major disturbance is moving toward Earth? And what happens when the magnetic field carried by that solar wind connects with Earth's magnetic field in exactly the wrong way? That is where the science becomes much more interesting, because the biggest challenge is not simply seeing the solar wind. It is understanding what the solar wind is carrying toward us before it arrives, and that is the part that scientists are watching closely.
It has not. The breakthrough is that scientists are improving the observation chain that tells us when conditions are changing. A new display will not stop a geomagnetic storm. It will not shield a satellite, and it cannot control the sun. But better measurements can lead to better forecasts, faster warnings, and better decisions. The next major solar disturbance could arrive months from now, or much sooner. Scientists cannot give us an exact date. What they can do is keep watching. And now, NOAA has another operational tool for watching the solar wind as it moves through space toward Earth. This story is not about fear, it is about preparation. And at Storm Producer, we will continue watching the science, the data, and the changing conditions above our planet. If you want to follow the next major development in space weather, subscribe and stay with us. Because the most important question is not whether the sun will become active again. It is whether we will see the warning signs in time.
But how much warning can scientists actually get when a major solar disturbance is moving toward Earth? The answer depends on where the disturbance is detected and what kind of event is approaching. NOAA's real-time solar wind observations are designed to detect changing conditions before they reach Earth. One important source is the ACE spacecraft, positioned near the L, one point between the Sun and Earth, roughly 1.5 million kilometers from our planet. Because solar wind measurements can be received there before the same plasma reaches Earth, NOAA says ACE can provide up to about 1 hour of advance warning for damaging space weather events. That may not sound like much, but in space weather, an hour can matter. It can give operators time to assess conditions and prepare systems that may be affected. Satellites can be monitored more closely. Radio operators can receive warnings. Navigation and communication systems can be watched for degradation. Power grid operators can also pay attention to changing geomagnetic conditions. And this is where the new solar wind display becomes useful. NOAA announced on August 21st that the display had completed its experimental review period and was officially moved into operational service. The experimental label was removed, and the solar wind product was moved under the observation section of the SWPC website. NOAA also said feedback from the experimental period would continue to be considered for future updates. The change may look small on a website. Scientifically, however, it represents another step toward faster access to operational solar wind information. There is also a second layer of forecasting. NOAA uses the WSA-Enlil model to simulate solar wind structures and Earth-directed coronal mass ejections. According to NOAA, this modeling system can provide roughly 1 to 4 days of advance warning for solar wind structures and Earth-directed CMEs. That is very different from the short warning available once the disturbance is already measured close to Earth. The longer-range forecasts tell scientists what might be coming. The near-Earth measurements tell them what is actually arriving. Together, those systems create a chain of observation. First, telescopes and spacecraft observe the sun. Then scientists identify disturbances that could move through interplanetary space. Models estimate how those disturbances may travel. Finally, spacecraft near Earth measure the solar wind directly before it reaches our planet. That last step is critical because the magnetic field carried by a solar disturbance can determine how strongly it interacts with Earth's magnetosphere. A particularly important factor is the direction of the magnetic field. NOAA explains that strong geomagnetic storms are favored when the solar wind magnetic field remains southward for an extended period. That orientation can allow more efficient transfer of energy from the solar wind into Earth's magnetosphere. This helps explain why forecasting a geomagnetic storm is not as simple as saying, a solar eruption happened, therefore a major storm is coming. The sun can produce an enormous eruption, but its eventual effect at Earth depends on several variables. Its speed matters, its magnetic structure matters, its direction matters, and the interaction with Earth's magnetic environment matters. That uncertainty is one reason continuous monitoring is so important. History gives us a clear example of what intense geomagnetic activity can do. In January 2026, NOAA reported that G4, or severe geomagnetic storm levels, were reached on January 19 after the arrival of a CME shock. NOAA said CME passage was expected to continue and that G4 conditions remained possible. But there is an important lesson here. A strong geomagnetic storm does not mean the world is ending. NOAA classifies storms on a 5-level G scale, from G1 minor to G5 extreme. Even G2 and G3 storms describe specific categories of technological and space environment impacts, not a prediction of global collapse. And right now, the broader forecast matters. NOAA's current 27-day outlook for August 17th through September 12th, 2026, says solar activity is expected to range from very low to low levels throughout the period. So the new solar wind display should not be interpreted as a warning that a catastrophic solar storm is approaching. It is something more practical. It is an upgrade to our ability to observe the environment between the sun and Earth. The sun will continue producing solar wind. Solar eruptions will continue to occur. Earth's magnetic field will continue interacting with that changing stream of particles and magnetic fields. And our dependence on satellites, radio systems, navigation, and space-based infrastructure will continue to grow. That makes space weather monitoring increasingly important. The real breakthrough is not that NOAA has suddenly made the sun predictable.